chi-squared. Now, this is what I really wanted to mention up here. No one ever really tells you this, right? But why is it chi-squared and whatever? Well, if x is a normal distribution, the sum of a whole bunch of x squares is chi-squared. So what it boils down to is this, is if x comes from the standard normal distribution of 0, 1, then x squared itself follows a chi-squared distribution with 1 degrees of freedom. That is literally what it is, which is why it's an x squared, chi-squared, x squared. That is literally what it is. It's literally what it is. What we use it for is basically this is the sum of observed minus expected values. So if we are comparing values, this will roughly follow a chi-squared with some degrees of freedom. That is more complicated. This approximation is relatively tricky to prove. I've tried to do it with 1 degrees of freedom. It's okay. With anything more than that, it gets really tricky. I've looked it up. But one thing that I want you to take away from this is really the chi-squared isn't just magic. It's if x follows a normal, x squared follows a chi-squared. And that's what it is. It's just the name we've given to this squared of the normal distribution. Now, where we're going to use it is when we want to compare stuff. So we want to compare values that we obtained versus values that we hoped for. And by and large, you can do this with anything. We're going to do it with distributions and with contingency tables, but literally you could do it with any set of numbers. You could have a set of 10 numbers that you are hoping to obtain, right? Frequencies. These are frequencies, right? Expected frequencies and observed frequencies. And you can compare them to what you actually got. And by and large, this idea fits.